Studying health online. And we're just getting the streaming up and going. Bring that down. And just display capture. That's that. Display capture. There we go. Okay, so right, debugging. So if we're going to talk about debugging, we can also talk about what kind of environments you're in. So we've already had Visual Studio over there. So you guys are using Visual Studio and debugging blueprints, right? Which is its own challenge. You guys, what IDE are you using?
JetBrains.
JetBrains?
So Sea Lion and WebStorm,
right.
LJ, etc.
So it's the full.
Yeah.
Yep. So and debugging technique. What technique do you guys use?
Their IDEs has integrated debugging, so it's kind of like Visual Studio where you can set watches and view variables and control the run flow.
So now in Visual Studio and in some of these IDEs, you can, when you put a breakpoint in, you can go into variables and change the variables at runtime. So does it allow you to do that? And have you used that in Visual Studio?
I've been on the use of it yet.
Right. Because in Visual Studio you can edit variables at runtime when it's paused. You can go in and change a variable.
I think you can do it with the JetBrains suite as well.
Right.
I think that's.
Yep. So in the JetBrains. So you are two different groups. Yeah. So you guys at the back. What are you?
It depends. We are using Atom for frontend, ESLint for
Right.
and then Eclipse and
Okay. So.
Java and React.
Right. And again, standard using breakpoints and print statements.
Now we have also static analysis on our queue. We
Okay.
use that first to check or get an idea of where we're going.
Right, because through a static code analysis, you can look for things that are likely to be a bit odd. So one of the things that static code analysis is quite good at is the sort of thing where you go, you know, if A equals B, static code analysis should tell you, wait a minute, that's extremely unlikely to be what you meant. Right? Just because, you know, that's always going to return B. Because it's not going to return false, it's just going to assign B and return B, and that's probably true unless B is 0. I wish it didn't ever let you do that. There are very few instances where what you meant to do was assign B to A, and if B was anything other than 0, do this stuff here. Right? I would have thought that that would have been done as a separate check, basically. Right? So so there's a concept in programming, and I don't know if you guys have been introduced to it, defensive programming. Have you heard the phrase? Okay, so defensive programming is the idea that you should code with the assumption that everybody who is going to look at the code is a moron, and that your code, that you are likely to make mistakes, and that you're likely to be looking at your code at 3 AM while you're trying to debug it, and you're therefore likely to do something wrong. So you should design your code and you should implement practices to minimize your chance of screwing things up. Right? So one of the things you do with defensive programming is that you assume that all input coming from outside of the program is unsafe and needs to be checked. Right? So you just straight assumption that, you know, if I ask for an int, it's probably not an integer. If, you know, I ask you to put in a path, it's probably got spaces in it, and it's probably got numbers in it, and it will be someone trying to hack my system. So basically you kind of armor plate your code against the user. Right? And I actually got a Skype in today from one of my former students who was doing a text test and who was in an interview, and he said the interview, one of the things that the interviewer said about graduates is that they didn't know enough about exception handling in C++ or templating, with the standard things that people weren't very familiar with, right, in C++. But also the idea of and throwing exceptions and handling exceptions in Java is, again, that's also a thing to do. And though, like, certainly exception handling is part of defensive programming and part of debugging, right? Because you can both handle standard exceptions, right? So there's a list of, divide by 0 exceptions that get thrown, right? You can also throw your own custom-made exceptions. Have you ever been taught how to do that and why to do that?
Yeah,
so you did in Java. You created your own exception throws and catches. Yeah. You can do the same in C++, right? Did you consider that part of debugging? Sort of.
Depends on the exception.
Depends on the exception. Yeah. So for debugging, because one approach to debugging, and it's one of the ones that I've got a link to here, is the idea that part of what you're doing when you're debugging is that you are trying to find the thing that isn't true, right? If your program worked exactly the way that your mind says it should work, right, then it probably wouldn't have a bug. So if it doesn't work the way you expected it to work, you've got to find out where it's going wrong. And so if there are 1,000 things happening, they should all be confirming, oh yes, that is doing what it's supposed to do, that's doing what it's supposed to do. That's why you guys do step-through debugging, because basically you're saying, yes, this thing is what I expected it to be. Oh yeah, and then it does this, that's what I expected. Yes, it does this, that's what I expected, right? It's when it does something you don't expect it to do that you go, wait a minute, no, that shouldn't be 0, that should be 1, right? Why is that 0 instead of being the 1 that I thought it should be? Right? So, to some extent, you doing debugging with step-through debugging, and your step-through debuggers, are doing this kind of exception handling yourself in real time in your brain, right? Because you're saying, I'm doing an assume, I expect this to be case good, I expect this to be case good, I expect this to be case good, this is no longer what matches. You throw an exception, you say, right, okay, now how do I handle this? Right? So you try and work it out by creating those in each individual step. You're creating your own set of what this the assumed next value should be. Because if you don't have an assumption of what the next value should be, how do you know it's wrong? Right? If you had no idea what the value should be, you just look and go, okay, now it's 7, great. Now it's 10, okay. So yeah, if you don't understand what it's trying to achieve, it's very hard to use a step through as a debugger. So this idea of assumptions and exceptions. So throwing your own exceptions and using assume in C++. Guys used assume? Assert rather. Sorry, not assume, assert. So you used assert and you made your program die when asserts failed?
Yeah.
And you've seen how code will fail on asserts in Unreal has asserts in it as well. And Unity, I think, both have asserts that crash when certain really bad things happen. Okay, so you guys have set through IDEs and have a way of editing values as you go. Okay, you guys, what environment are you working in?
Probably Java.
Okay, so IntelliJ and Java, right? And so Java has a debug logging class, right? So you can actually use the standard debug logger, and you can log to debug, and you can log it at various levels, and yeah. So you've used the debug logging in Java?
I haven't really started with the coding yet.
But you have used it in the past, I mean.
A little bit, but not a lot.
A little bit, but not a lot. And guys, in?
Android Studio and Java.
Android Studio and Java, right? So there's a few things to think about, and as you say, static code analysis can help. this? So static code analysis is the and have you guys included coding style in your static code analysis, or are you just using SonarQube by itself without a linter attached? Right? Yeah. Okay, so just default. Yeah. So it picks up some things like that. It'll pick up the if equals thing pretty easily. It'll also look for bracketing around for loops and things, and so it does a bunch of those standard things. One of the things that we used to do, and you can still do with your defensive programming approach, is, and some of these are coding standard stuff that make it easier to be debugged by having more certainty in particular lines of code. So if you would say, if A equals 10, then do something, right? So if you had a magic number somewhere, then, and you know, that is somewhat easy to miss one of those equals and suddenly A equals 10, right? Okay. However, if you program the other way, so you put your statics first, if you miss out one of the equals, your compiler will go, no you can't, because you can't set 10 because it's const. Right, so just by putting the constant thing on the left hand side, it means you can't fail with this particular comparison. Right? Now, if you're going to do this properly and say, you know, B equivalent to A, and so you have int B up here, right? If you're doing that, then it will go, no, you can set B to A, right? So that won't save you, right? If you've taken out the magic number and you put it where you should do, up the top. So the defensive way of doing this is say, yes, this may be an integer, but it's const. Right? You define it as const or static or whatever the particular keyword in your language is, but you tell the compiler, no, this won't change. So when you do that, it goes, no, you've said it won't change. You can't change a const. Right? So there are some little things like that, which if you get into the practice of doing, decrease the chance of some of those simple finger typing errors, right? And copy and paste errors, because copy and paste errors are some of the hardest to find. Right? Because when you copy and paste things, because you've seen the pattern before, your brain assumes that the pattern is still the same, or it should be the same, or like the little changes don't matter. And so those sort of things can be very hard to go through and find. So as you can see up here, we have, I'll go to the page. So in the testing, I was just looking at this before I came because I was, and I didn't save it at home. So I didn't save my changes to this page from my at home where I was editing it. Right, so I will go to maybe I can get my history, because my history will probably have been updated. History on that one. There's my edit. So if I go to history and I go to my, I need to see more. I need to see it's the tab under that one. Yeah, should be able to open the whole folder. And so just before I came, where is it? Google Style Guides, CM Style Guide, login, the art of debugging. Okay. Yep, you can turn that one on. So I had been looking at the art of debugging just earlier, and this particular is a chapter in a book on the art of debugging. and I was supposed to have updated the Confluence site with it, but I didn't hit save when I was at home before I came up. So if you look at the, I mean, you can do the search for the art of debugging online, but you can go. I'll put the link into the web page as soon as I'm done. But so in that they go through and the other principles of debugging, although you might not be able to see those easily. So if I make those big, right. So one is the assumptions. The others are start small, right? So debug small parts and simple cases. When you have a bug that you want to share on Stack Overflow, because I assume you guys mostly use Stack Overflow. So one of the things that I'd looked at for this course, which I have suggested to students before, and we haven't quite been able to properly organize, is that if you have a particularly challenging bug that you can't find the solution for, do write a Stack Overflow question for it. Right? Make your new Stack Overflow question. Because even if you think that I'll give you the answer, which I might be able to, but if we put it up on Stack Overflow and you ask your interesting question there, and then I provide you an answer, a potential solution to that interesting problem, I can put it on Stack Overflow, but you might get other people's even better answers. Right? So I can suggest something on Stack Overflow. Part of the reason for doing this is if you find a bug that you can't find a simple solution to on Stack Overflow, then maybe that's a bug that other people are having and can't find a solution for. So if we do find a solution for it, you've helped the community of people who are trying to debug programs. Okay, so contributing to the debugging community. A lot of you probably use Stack Overflow, or at least have Googled and found Stack Overflow answers to problems of installing things. And yes, versioning is quite important when you're making Stack Overflow questions. And starting small, one of the things to do when you have a bug you don't understand is to try and replicate that bug with the smallest possible version of your program. Right? So you strip away as much of your program as you can and get it down to its smallest possible unit, replicate the bug there, and then try and work it out. Right? So there are fewer other things going on in the background and fewer overheads before you get to your bug. Right? So when you've got a really challenging bug, that's one of the things you do is you keep turning off subsystems and checking if the bug's still there. Right? So you just get rid of stuff until it's got down to the simplest and smallest thing. Right? So first, yes, as it says here, yes, if your code consists of a large loop, the easiest bugs to find are those that arise in the first or second iteration. The nastiest bug I think I've ever had to track down in my own code, right, was I was doing neural network code, and I had allocated the wrong size to my input file, and it wrote over my weight matrix for my neural network, but it read in to the bottom corner of the weight matrix. And because I'd read the file in and then parsed it, so I had to, so I need to draw this, right? So how this program worked is I had allocated memory for the neural network, which had a whole bunch of integers in it, and then I had allocated memory for file reading, and then I had allocated memory for the processed patterns that I was going to use. Now what file reading did is file reading wrote into this area because it hadn't been allocated enough space to fill up its own thing, so it kind of wrote over my weight matrix. I then processed those, that I chunked them into the individual patterns that they needed to be, and put them over here. Right? So that was fine. Then I went and initialized my weight matrix, and I set it to 0. But I only initialized the top half because if you have an A connection to B, and you say it's symmetric so that B is the same, has the same weight to A, then then the number here is all you need to know, because like if this is well, I suppose this is B and this is A and B, the AB connection here is the same as the AB connection there. Right? So you can actually, I suppose, that is actually that way. So I was using the triangle of AB connections because they were going to be symmetric across that area. Right, so okay, that's fine. That's how I do who's connected to whom. And what I didn't realise is that because I had just cleaned this space out and I was updating this space, my for loop was actually running through the whole list here. Now, when this file was small and only wrote into its own space, these were all zeros and stayed as zeros, so when I included them, they were all zeros, so they didn't affect anything. Right? Because I was multiplying stuff by zero and everything was fine. However, when this file got very large, it then overwrote into the space. All of the numbers I thought I was using, I checked, and they were all right, and everything was fine. And it was in iteration about 1,000 through my learning loop that things started to diverge from where I thought they should be. And doing step through on about, because this was 50 units, so it's a 50 by 50 matrix, and so you're doing 50 squared operations per loop, and you have to do 1,000 of those, and you have to step through them. You're thinking, I can't step through that. So it took me a long time to find that particular buffer overflow, because it only happened on very large files. If the files happened not to affect these numbers in ways that mattered, then it didn't matter. And it was because I hadn't done a for loop that only looked at this part of the file. Right?
It's a very good case for conditional breakpoints.
Yes, conditional breakpoints. Oh my, I would need those. I didn't have those at the time, so I didn't have conditional breakpoints, and it took me a very long time to find it. It also is one of those situations where if you do have your debugger initializing everything to zero, but your runtime leaving them whatever they were, you hopefully would immediately notice it, because that would be every time you went to release, it wouldn't work. Every time you're in debug, it would. But for this case, it was if it's a file that's of a certain size. Right? So yeah, that took me about 3 days to find, and man, that was annoying. Yeah, so it still pains me, even though that was 20 years ago. More than 20 years ago. So yeah, so trying to replicate your bug and keeping things small, and the first or second iteration is good. So this chapter goes through use a top-down approach. There are user debugging tool to determine the location of segmentation faults. So you've heard of electric fence? The concept of electric fence? I see vaguely glazed eyes on the concept of electric fence. Okay, so again, individual programs, right, will give you individual kind of things you can do. So, but with debugging, I think if we teach you concepts, because the tools will change, right? So the tools you have in your different languages will be different. You just have to go and see what all the things you can have. With your static code testing, if you use your linting, so you say what you encode your programming language style into your static code tester, that might also help you find some common bugs if your coding standard stops you doing certain particular things, right? Say, in our standard we never do this thing. Oh, I did that thing, that could have led to the bug. One of the things with memory allocation, the concept of electric fence, I think is what's important here, is the concept of building a wrapper around what you do to evaluate, to kind of evaluate what's going on. Right? Now, if you're using Visual Studio, it has a profiler, and the profiler has multiple types of profiling, but two of the main ones are instrumental or sampling. Right? So instrumentation or sampling. If you use instrumentation, what it does is it puts every function call. So if you go, you know, get new input, right? If that was a function that you were calling, then instrumentation actually creates a new function call. Basically, what it does is it says, okay, for every time you call a function, what I'm actually going to do is I'm going to create a new function called underscore get new input, which has parameters. And when you call get new input, there will be a function here, which is function get new input. And it will take all the code that you had inside this function. It'll bring it down and put it inside this new function with double underscores, get, and it'll do an increment on the vector of functions called. So if you had functions called as a vector, and it goes get new input plus, it will increment the number of times you've called that function, and then go and call the new one it created. Right? So it just put a wrapper around your function to say, every time you call this function, I'm going to do some other code to increment when you did it, to increment how often you did it, and it will also do things like functions called, function time, start, and it'll use the get new input, and it will set dot now kind of thing, and then when it's finished it will call function called function time end. Well, actually probably doesn't need to set the end, it probably just does a calculation based on that, which says, you know, function called time for get new input increases by now minus that thing. No? So it wraps a timing loop and a number of calls loop around every function. Okay? So that's a concept where, although now the external code looks like it just calls whatever function you created, right? So you've got this function, your code says get new input, it does its job and returns all of those. It's just internally what it's doing is added all of this additional checking code and logging code around the function you called. Right? Now, if you use profiling tool, it will do that for you, right? So you don't have to manually do this, because this would be extremely annoying to have to write all of this code yourself, right? That you generally won't do that. But this concept of saying, okay, if I've got something that I'm working with and I want to inspect it and I want to protect it, or I want to understand what's going on with it, what I'll do is I'll put a wrapper around the actual function and just present this wrapper to the outside world. So what electric fence does is it does this for arrays, except it looks at arrays and says, okay, so with an array I've got a bunch of memory that have been allocated. Given that I know that one of the standard problems is that you step through an array, what I'll do is I'll actually shift your array and I'll put two entries, one at the front, one at the end, and if you ever touch either one of those, I'll have an assert fail. Right? If either one of those, that piece of memory gets touched, bang, you stepped outside your array, you're a naughty program. Right? So the concept is, you create a new, when you create your array, you don't get the array you thought you were going to get. You get an array with bounds checking on it, with these like the electric fence, the fence on the outside that has monitors on those values. And if you touch them, if you're an operating system, you can actually set it up to if the memory is accessed. If you're not in the operating system, then you could do things like if you try and change those, right? If you ever write to those, you can go, wait a minute, that value's changed, bang, I'm going to stop you, whatever you're doing. You won't get a seg fault, right? Because it won't be the operating system telling you, oh, you've hit the end of your segment, you're not allowed to print there, so I'm going to crash your program, right? Which is what you don't want your program to crash. So what you do is you internally can say, you've tried to step outside of that array. Instead of letting the operating system stop you, I'm going to stop you because I've been monitoring that piece of hardware and asserting it's always going to be the same. Right? So it's this idea that I can put wrappers around things and create checks that stop you doing bad things, like stepping over the end of an array. Right? Now, in game design we talked about, and in game programming we actually talk about some design patterns, and part of the reason to use design patterns is they help you with this being sure you're doing the right thing. Alright, so one design pattern is to have factories, so all memory creation happens in one place and only one place, and all deletion happens in one place and only one place, which means if you want to add wrappers around memory you've created or memory you're destroying, and you want to see who's destroying and creating memory, there's one place you go to do all of that. Right? You go to the factory, you change how the factory creates things, and you can monitor what's going on. In that mode, you guys use step through debugging, right? So you fire up your debugger and you're stepping through. So do you often use print statements or print things to console? You print things to the debug. Yeah. The concept of debug levels, have you used that concept?
Like warnings, errors.
So you've got the warnings and errors, which you, for console output, they actually, originally in C and C++ on Unix, you actually had, those were different output, basically files, that were going to console, right? So error and warning and things were of different levels. Right? Now you can also create your own debug logging class, and it can be a useful exercise to understand how debugging works, is to write your own debugging class, right? Because what you say is, if I'm looking at doing a debug, if I create a debug class with .log, that's just a function call which takes a string, right? And you could write that class and the function log, right? And then during compile time or during when you're running, you can set values inside your debug class to log more or less things, well, more things or fewer things, right? So you can raise and lower. So because at the moment what you generally do is you just do debug log, and you can do, I think within Java debug you have it as a like comma warning, or I think you add it as a parameter in here, which one it goes to.
Log dot and then EI.
Right, so yeah, so it's yeah, you can say where it goes in its debugging. You of course can add things to that and put a wrap around it and do your own thing and add your own levels, right? So instead of pre-deciding what the debug level is going to be, instead of using printf, so you use this debugging in the logging tool and you raise and lower what levels of debug you're interested in, right? So you could even, for you, if you've got I've seen people do this with individual developers, can have their own debug log statements, right? So I could have, you know, if I had a parameter, I could add Simon, and if I turned on Simon's debugging, then all the debug statements I had written with my tag in them would be showing, right? So I could customize some of my debug, so it wasn't just generic, it was related to. Now, you generally wouldn't use Simon, you might use a function like, you know, UI. And if you want to debug all the UI instructions, then you can turn on the UI debugging, and it will give you those. Right? So you create classes of information. Now, if you're following this approach of saying, oh, okay, so I'm going to have function calls, and I'm going to have UI debugging, you could write wrapper functions. So when you write functions, you create in the first part of a UI call, UI show, in the first lines of your function, you could have, if you're in C++, you can have ifdef. You can use if defined debug, right? You could add standard tracking information on where you wanted it to be in the program. Right? So it just adds little bits of header information, and then when you want to show the flow of your program, you get it to do this, and it will show out to the output the flow of your program. Right? So if you know you're going to debug things often, then adding this kind of wrapper or adding default things into every time you do a function call is just your standard approach, is to add this logging information if I'm in like logging mode. If I'm not in logging mode, it all gets compiled out, and so I don't have the extra overhead of it. But if I'm in debug mode, it gives me a kind of trace of the program so I can see what's going on. And so it's just sort of simple things that when you put them in, you can leave them in if you've put them in with this kind of situation. Because I assume what a bunch of you do is you'll do a debug log and then you will comment this out. Do you comment out do you like do double comments and comment out your debug, or do you just delete it? You delete your debug logs, you comment it out, and then it's full of commented out debug calls. In Java, do you guys comment out your debug logs or just delete them?
I usually write a function that has an if statement, so if debug.
If debug. So you write a statement here that calls a debug function.
Yeah.
That's if debug, then log, otherwise don't. And so you leave that call in there. Yeah. So that allows you to turn it on and off when you need to. Now, what you can do is that rather than just turning it on and off, you can also set levels and set tags and do those comparisons. Right? So that's the nice way of kind of keeping that work in case you need it again. So, because what I'm trying to, so the principle there is that you should be thinking, okay, how do I wrap things? How do I find out information? How do I predict, or how do I find out what my code is doing, and how do I make sure that it's doing what I think it should do? Now, here they talk about, you know, segmentation faults. So some code doesn't have segmentation faults, right? So some things just won't allow you to do things outside your segment. So so this is more in C++. Determine if the location of an infinite loop by assuming by issuing an interrupt. So as I said before, when you can set the value of a variable, you go into a loop and you set it at the terminating value and then see if it terminates. Right? At least then you can see, oh, it does what I expect it to do when I give it a terminating value. Binary search. You guys understand parameter binary search? Right? Because if something's going wrong, rather than changing your number by a small amount, the idea is that you should use double and half is this approach. So if when I put in, you know, 10, it gives me an error, right? And I'm trying to find like a when's the error occurring. I can try 20. If it's still there, then I can double to go to 40. And so I don't go try 10, then try 11, then try 12, then try 13. I don't sort of incrementally search through parameter space, you double and halve looking for what's going on. Right? Now, for your very first search, you might decide, okay, 10, let's go to 100 and see if it's still a problem then. Or if it's not, yeah, if I know that it's a problem at 1,000 and it's not a problem at 10, then I could try 100 and use a kind of log2 approach, or I could try 500. Right, but I'd probably try 100. If it wasn't a problem at 10, it was a problem at 1,000, I'd say, okay, maybe it's a problem at 100. No, okay, then I'd probably go, then I'd go 500. Right, once again, within an order of magnitude. Right, so it's kind of the first layer I would use is, well, in this case, a log 10 scale. So big jumps. And then when I'm within order of magnitude, then I go into binary search. Right? Because some effects are log 2 based or log 10 based, and some effects are kind of just you're trying to find the individual linear scale, and then using a binary search is a good way through that. So changing parameters, how you do searches through parameters, how you look for those, and they describe this as an art rather than a science, because if debugging was purely a science, we wouldn't really need to do it, because we probably would have implemented programs that did it for us. Right? If it was completely obvious what you needed to do and there were set steps that were clear that you did, then why would you need humans to do them? Right? You just program an algorithm that would find it out. And like Sonar, they're trying to do that, right? They're trying to make programs that will statically check your code. But even then, it kind of hints where things might be, and you still have to check them. Right? So sometimes it gives you orange flags on things which are actually perfectly fine code. You just haven't done it quite the way it would like you to. So looking through here, text-based versus GUI debugging. So you guys are all using GUI debuggers, or have you used GDB and a text-based debugging? Right. So who uses GUI get tools, and who uses command line get? Command line get over there. A combination. I use a combination, right? And in fact, one of the things that I do with my semantic commits, I find the GUI is better for extracting individual lines of code. Is easier to do in the GUI than it is to do in command line. You can do it iteratively in command line, and I can show you how to do it iteratively in command line, but it's massively annoying, right? Because you have to go step through each file, seeing each diff, and selecting each part of each diff to build a change set that you're then going to commit. Whereas in the GUI, you go, oh, click, 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 done. So in the GUI, that kind of selection of your change set is much easier than the manual stepping through that you do in command line. However, almost everything else you do in command line is faster, so it's a trade-off. Okay, so it's now 3 o'clock. We've started the discussion on debugging, right? And this chapter continues, and this is a book on software quality. So you can read whole books on how to make better software. This is the debugging chapter. So when we get back, we can have a look a wee bit further through this and discuss some of the challenges. And also, if you have codes in so your networking code, we can have a look at some of the standard techniques for attacking network code. Do any of the rest of you have bugs that you'd like to kind of discuss how to track them down?
I was writing a chess engine.
Mm-hmm.
One of the things you have to write is the move generator. So
yep.
With single state you create all the possible moves. And the way you debug them, or the traditional way, is to generate every move,
yep.
like 7 layers down, and then you have around 130 million moves. And you see, like in a database, if you hit the total, like if you're one off, you have to find the error.
Right.
Yeah, but that's it. You don't have any more than that. So if you have a suggestion.
Right. So, okay. Well, we'll have a break so that I can think about that, and we come back. We can talk about how you might approach that and how you can approach the networking issue. Because again, finding an individual bug is a challenging activity, but it's building those techniques for you guys, right? So that you have, how do I break this problem down? How do I think about debugging this challenge? Okay, so have a break, go and walk around for 10 minutes, and we'll see you back at 3:15.